Good morning, good afternoon, or good evening, everyone, depending wherever you're based. Thank you so much for attending this session. It's one of many developer-focused workshops we got coming up over the coming weeks. Today is all around an overview of blockchains, how to write your first smart contract, as well as diving into the various different kind of consensus mechanisms, and dive deeper into Ethereum, Bitcoin, etc. So just going to go over a few housekeeping rules, just to let you know that this particular session is recorded. We will be sharing a copy with you sometime next week, together with the slides. And then I also encourage everyone to post their questions on the chat message. My colleagues will be keeping an eye on that. And then feel free to interrupt us with any questions throughout the session. And then if we have any spare time towards the end, we'll also do a Q&A with Laurence. I think that's it from my end. So over to you, Laurence.
Great. Thank you, Antonio. Thanks for inviting me to this session. And thank you to Endorse and the other partners for setting this up. I hope everybody's really excited about the hackathon. It's great to see so many people interested and excited at getting involved with blockchains. I'm really looking forward to seeing the projects that you all come up with. So I'll just start off a little bit about myself, my company. I'm the CEO of Extra-P. We are a blockchain consultancy. We've been running for just over 5 years now, providing blockchain solutions, doing development, writing a lot of smart contracts. But we really enjoy also community education, and we've done lots of developer workshops. Together with Antonio, we've been doing those for about 4 years now. Really enjoy doing those. Today's workshop very much about giving you ideas and some information and helping your skills around what you will need to use during the hackathon. If you have questions, please do ask. I'm happy for you to interrupt. I may not see things coming up on chat, so if Antonio or Richard, someone could interrupt me, that's fine. If there are questions, I'm happy to answer those. Okay, so what we will look at this afternoon, I'm going to start off with a little bit of theory about blockchain and decentralized systems. We'll go through a consensus mechanism to show how that works. I think that's always very useful to answer a lot of people's questions about blockchain in general. We are assuming that you do not have any real knowledge of blockchain before you start this afternoon. So we are really starting from scratch. I'll go through quickly how Bitcoin and Ethereum work. And then we will have a think about what makes a good blockchain project. So as you're doing your hackathon project, it's worth taking some factors, some aspects into consideration when you're deciding whether you're going to be using blockchain or how you're going to structure your project. Then we will get some hands-on experience writing some smart contracts using a tool called Remix. This is an in-browser IDE. And then I'll talk a little bit about the design of applications, and then we'll have plenty of time for Q&A at the end. So you can either ask questions as we go along, or if you would like to save the questions up till the end, that's also fine. Okay, so let's start by thinking about decentralized systems. And really, I see the innovations and the rise of blockchain technology as part of being a wider movement towards decentralization. And this, some of the systems we have are to some extent decentralized, some are centralized. It may not be clear where things lie, but there are aspects of each that there are some properties that we can say about each type of system. Now, I think one of the reasons that we're moving towards more decentralized systems is the fact that our world is becoming increasingly connected. Um, we all use, we use social media. We are connecting to each other much more than happened 10, 20 years ago. And this increases the complexity of systems. And this is something that centralized systems find hard to cope with. They are, to some extent, quite fragile in the amount of complexity they can handle, whereas decentralized systems tend to handle this better. This slide I'm showing here, I've taken a table from an interesting blog post. I recommend you read it. There's a link to it, which looks at, which compares decentralized and centralized systems. And there are advantages and drawbacks to each. As I say, decentralized systems tend to be more flexible and resilient, whereas centralized systems can often be more fragile. With a centralized system, there will be some degree of some central authority that you will need to give authorization to, whereas with decentralized systems, you can have some kind of sovereignty over your abilities in the system or your data in the system. Decentralized systems can suffer from inefficiencies, though. It may be more difficult to make them scale, and they may be more difficult to manage than centralized systems. Okay, to help get your head around how to think about decentralized systems, and certainly if you're going to be writing applications on the blockchain, this is something that you'll need to do. I think it's useful to think about, imagine you wanted to play some game with some friends. And I mean, this is something that may be quite relevant at the moment. A lot of us around the world are having to meet, as we are today, remotely. Because we cannot meet in person. So if you imagine you want to play a game with some friends, but you cannot meet in person, and the means that you can play this game will be perhaps via phone or email, and there is no online version of this game that you can go to. So already what I'm trying to say is there's no central authority here. So we're very much thinking about playing this game in a peer-to-peer manner. So some games do this successfully, and people do, for example, play chess by post or by email, as well as doing it online. And this works relatively well. They can communicate their moves to each other, and they will typically set up each person would set up a board, and then they can move the pieces as the moves come in, say via email. And each person can check when they receive a move, they can check that is a valid move for the person to make. And if, for example, it's the move is being made by email, then you have some confidence that the person that has sent you the move is the person that you intended to play with. So there is some degree of identity established there. And you're probably fairly confident that nobody is impersonating that person or tampering with the moves as they come to you. If we think about moving to a more complex system, a more complex game, such as Monopoly, perhaps we would do things in a similar way, although it may be a little bit more difficult. But again, we may well have our own board. Every person who is playing or every person who is participating may have their own board, and they would keep a copy of the current state of the system. So as people make a move, they would move the pieces around. So you would ideally have everybody who is playing would have some synchronization about the state of the system. Their local copy would be the same as the copies of everyone else. But you may run into some problems. So in terms of making the moves, if you follow them closely, then you could probably track the amount of money that each person has. It would be a little bit more difficult perhaps than, say, in chess, where the state is simpler, but it would still be possible. But then we would also run into problems such as verifying, if someone is throwing a dice, verifying that what actual number they came up with. So as the things are becoming more complex, this would be more difficult to do. But the sort of takeaway point from this thought experiment is the idea that the participants would all have their own local copy of the state of the system, and they would be following the rules that they would all have agreed upon, and they would be able to tell if, certainly with chess it would be easier, but if someone tried to make an incorrect move, that would become obvious, and people could disallow that. So having thought about that and thinking about how you can move to decentralized systems, let's think now about blockchains themselves and what are the typical components of a blockchain. Now, if you, it's early afternoon, maybe you've just had lunch, if you're feeling a bit sleepy and you fall asleep before the end of this workshop, that's fine, but please take this away if nothing else. The important thing to remember about blockchains really is the fact that they can establish trust between participants. They can establish this trust layer without a central authority. And if you keep in mind this fact that there's no central authority, that really will lead you into understanding how these systems will work. And particularly when you're creating your applications in the hackathon, I expect you will, if you're used to developing traditional applications, you may well come across this again and again, where you're thinking about doing something, then you remind yourself, oh no, there is no central authority, we can't do it that way, or there is no central process running here that we can rely on, we have to do things in a decentralized manner. Okay, so typically in a blockchain system, there are a number of components. Now, the ones I'm going to feature here are the ones I think are particularly important. Other people may disagree, have different emphasis. I don't know if there is a canonical list of the components making up a blockchain. You may have your own views, but I think one of the important things is the idea of a gossip network. Now, in case of blockchains, we use typically a peer-to-peer network built upon the internet. And the reason we call this a gossip network is that the participants in the system, as they receive transactions or information about the changing state of the system, they will gossip this information around the system. They will pass this information on to their peers. And typically these peers will not be close geographically, they may well be remote. And there is some degree of trust involved here in the fact that the peers will pass on this information. And there are protocols established around this so that if peers are withholding information, maybe they will be dropped by the people that they are talking to, and those people will then talk to people that are more cooperative. But that's the one basic component of a blockchain, I think, is the idea of this gossip network, where transactions and information can flow freely through the network via the idea of the participants gossiping the information around. And with public blockchains, this network is very much ad hoc. You do not need any permissions to join this network. And if you leave the network, that doesn't cause a problem. People can join and leave as they see fit, and the network as a whole will still function, and new connections will be established between the participants. The next important component, and perhaps the most important component, is the idea of a shared public ledger. So particularly if we're talking about public blockchains, this will be public. The idea of a ledger, these are come from banks with typically large books where every transaction was recorded. In terms of a blockchain, we have a similar idea. So each participant in the blockchain will have a ledger in which they can record all of the transactions that they see upon the system. So if we think about our game of chess or our game of Monopoly, really this is very similar to the board, or the pieces on the board is something that everybody has a copy of, and that is the state of the system at a particular time. And we will have means of updating this ledger, and this is done via a consensus mechanism, and is done via consensus of the participants within the network. The third part, the third component that is involved, I won't go into that in any detail, but that is important, is cryptography. this is because on the internet it is relatively easy to impersonate people or lie about your identity, or to manipulate transactions, or to tamper with them as they go through the network. And so we use cryptography, cryptographic protocols and techniques to ensure that we can have some idea of the identity of the person we are interacting with. And this may well be a pseudo identity. It may not be an identity that we can that is established in the real world, but we will be able to have some identifier for the person within our network. And also we can have some confidence that sorry, I'm just trying to admit people into the waiting room. Also, we can have some confidence that transactions that are flowing through our system haven't been tampered with. So typically we use cryptographic techniques to get a fingerprint of a transaction that we can then verify at either end of our system. Now, the next these components that will then typically give our blockchain a number of features. So because of the public nature of the ledger, and the fact that our transactions are being transmitted freely through a gossip network, we get a transparency to our system, and we can be sure that the state of our system is verifiable by the participants. So every participant will receive every transaction in the system, and they will be able to verify that updates to the state of the system are happening correctly, and yes, if the gossip protocol is working correctly, then there will be everybody will be able to see all of the inputs into the system. Because our network is ad hoc, it will have some resilience. So if particular participants drop out of the system, that will not affect the system as a whole. If data centers go down, the system will probably survive. But also there's the idea of censorship resistance as well. If a government decides it doesn't like your blockchain, it may be able to shut off all of the nodes of that blockchain within its jurisdiction, but nodes outside its jurisdiction will be able to continue. It's very difficult for any company or any government to censor what is happening on a blockchain. And also, because of the cryptography, we have the idea that the interactions we have will not be tampered with. So if somebody has a wallet and decides to send a Bitcoin to somebody else in the system, if we see this transaction, we can be sure that that is the transaction that came from the wallet, and it hasn't been interfered with or manipulated. The amount hasn't been changed as it goes through the system. Now, this next diagram is an idealized diagram about, to give you an idea of what a ledger might look like on a blockchain. Now, all blockchains will actually store their data differently, but this is an idealized idea of what blocks may look like, and it's useful for thinking about the security of the blockchain and what makes a blockchain special. So the general idea is that we start off, the blockchain will start with a block 0, usually called Genesis block, and after that, blocks will be added at a particular rate. In Bitcoin, this is around every 10 minutes. In Ethereum, it's every 12 to 15 seconds. And after this particular time period, the transactions that have appeared in the system will be gathered together into a transaction area of a block. To this, there will be added a header area for that block, and the header area will contain a fingerprint of all of the transactions. It will also contain a timestamp to show when the block is being produced, and it will have a pointer back to the header of the previous block. It will have effectively a fingerprint of the header in the previous block. And this gives our blockchain, this gives our data structure a great deal of resilience here. Because if you imagine that somebody comes along and tries to introduce a block, tries to send you a block and claim that this block is a block that belongs in your blockchain, and it was a previous block, then if they have changed the transactions in that block, then they would also have to change the header of that block, because they would have to update the fingerprint that came from the transaction area and is living in that is in the header. But if they change that header in one block, then they will have to change the fingerprint of that header in the next block. And so therefore, if somebody tries to change the transactions in a particular block, they will have to change all of the blocks after that point for the blocks chain as a whole to still make sense and to still be verifiable and still have some integrity. And in the case of blockchains like Bitcoin, there is the work happens when you're creating blocks, and this work has an economic cost. And so if you wanted to make changes to a great number of blocks, this would involve a great deal of work and a great deal of economic cost. So the blockchain, the security of the blockchain for Bitcoin, for example, is guaranteed by the economic disincentive that you would have to changing any of the blocks. So if you wanted to tamper with this blockchain, it would cost you a great deal of money, and that's where there's the security of such blockchains comes from. So let's look at one of the consensus mechanisms and see how we arrive at consensus throughout our system and how we actually produce blocks. And so this is the consensus mechanism that is used by Bitcoin and currently by Ethereum. And it should give you a good idea of how decentralization works. And it was this mechanism that really was the breakthrough that allowed us to have our first real blockchain when we had Bitcoin. So the idea here is that this diagram is meant to represent a number of nodes on our system. These are the black dots, and they are connected together in some ad hoc manner. And the bottom there, that blue block, is there to represent the latest block in our system, and that represents the absolute truth about our system at a particular time. So all that we want to know about our system, you can take from interrogating the blockchain by starting at that latest block. And that really is the ultimate source of truth within our system. And you may, even if you disagree with what's held in that block, well, unfortunately, that's unlucky, because that really is the only source of truth we have within our system. Now imagine within our system here, we have Alice, and she wants to make a transaction. So she will make some transaction. She will create this transaction. She will sign it cryptographically to show that it came from her. And this transaction she will send to a local node on the system, on the network. And at this point, a gossip protocol will kick in, and the nodes will start to gossip this transaction around the system to the other nodes. And then at some time after this transaction has been started to be gossiped around, it will be gathered along with other transactions, that have been introduced, and it will be put into a block. So here, the yellow block, and that yellow block will be added to our blockchain as the latest block, and will represent the latest state of the system at that particular time. Okay, and as time goes on, we will continue, and another block will be produced by different participants, and our blockchain will move forward with different transactions appearing each block, and the state of the system progressing over time. So that's all quite straightforward, and we have the absolute truth of our system represented in the blockchain that everybody will receive. So everybody will receive each of these blocks. But then we have to think about the situation that we could have here. So it may be possible that some transactions are introduced into one part of the network, and these are progressing and moving throughout our network. And as that is happening in one part of our network, in another part of our network, some other transactions have been introduced. And so if we take a sort of snapshot at a particular time, we have a situation that we don't really want, because we're looking to have everybody in agreement about the state of our system. We want consensus about the state of our system. But if we look at the network at the moment here, we have people with differing views about our system. So some people will see the grey transaction. Some people will see the green transaction, and some people will see neither transaction. So how do we arrive at some consensus? How do we arrive at an absolute truth about our system at this particular time? And the way that we do this is to say that, well, all of the nodes in our system are effectively equal. There is nothing special about any node in our system and any node's point of view or any node's view of the transactions. So why not pick one of these nodes at random and then say, we will take your view of the system as being the truth about our system at that particular time. So we'll allow you to create a block, and whatever your view of the system is at that particular time, whatever transactions you have included in that block, we will, as a whole, accept that as being the state of our system at that particular time. And then a little later, we will take somebody else's view. And if we pick these people at random, then this will be done in a fair manner and nobody will be able to manipulate the system. And that's great. So a great idea that would allow our blockchain to progress and allow us to come to consensus about our system and about the state of our system. But of course, the problem here is that we have no central authority to do the picking of the random node here that is going to produce the block. And so the question arrives, apologies for the noise, the question arrives then, how do we pick one person at random in our system to produce a block, to create the latest state of our system? And the way that we do this in Bitcoin and Ethereum is that we allow people to participate in a race. And it is a race to solve a puzzle. And the nodes in the system do not have to partake in this race. If they don't want to, they don't have to get involved with producing blocks. But if they want to produce a block, they must take part in this race. And they are incentivized to take part in the race by being given a reward if they produce the block of a certain amount of the native cryptocurrency of the system. So in Bitcoin, they will be given a certain number of Bitcoins as a reward for producing the block. And this race involves solving a mathematical puzzle. It is an extremely difficult puzzle to solve. And it has been designed so that there is no way that you can really take a shortcut in solving this puzzle other than by just making guesses at certain values. So if you want to take part in this race and solve this puzzle, what you do is you just run some software that makes guesses as quickly as you can at certain values. You take this guess and add it to data that you're going to put in the block. You run that through a cryptographic function called a hash function. If that comes out with a value that meets certain criteria, in this case, if it's small enough, then you're thought of as having solved the puzzle. What you do if you solve the puzzle, if you guess one of these values correctly, then you can put the answer, you put your guess into the block, along with all the other pieces in the block, so along with all the transactions that you have seen that represent the state of our system. You then send this block out to the network, and the people that are the other people in the network will receive this block. They can check whether the answer that you guessed is a correct answer, so they can check that you have done this accurately and you haven't cheated in any way. If you haven't cheated, they can check the transactions in your block make sense. And once they're satisfied with your block, they will accept it and they will add that as the latest update to their local version of the ledger. And so as the block goes around the system, everybody will update their local ledger with the latest block. So the whole system as a whole will then get updated with the latest block. Now this puzzle is, as I said, very difficult to solve. So even though on Bitcoin, there are many tens of thousands of people who are making many billions of guesses every second to try to solve this puzzle, it still takes on average 10 minutes for one person in the world to come up with a correct answer to this puzzle. And so that's why the block time on Bitcoin is 10 minutes. On Ethereum, the mechanism is slightly different. We have a much faster block time, so it only takes about 12 to 15 seconds for someone to solve this puzzle and to produce a block. Different blockchains do this differently, and may well use different consensus mechanisms. They may well not use a puzzle like this to choose who produces a block. But it is useful for you to bear this kind of idea in mind, and this idea that the participants in the system are arriving at consensus in a decentralized fashion, and that there is no central authority here producing blocks or dictating what the state of our system is. It is the state of our system is arrived at by consensus and by agreement amongst the participants in the system. And all the participants in our system have agreed rules about what a block should look like, what the rules are around transactions. So they have an agreement around the protocol that they are following in the system. And this was really the breakthrough that happened when Bitcoin was introduced. And this was the real first practical way that we had of building a blockchain and building a really decentralized system that could function at scale. Now that's all good, but there is one further problem that we may come across, because as the people who are doing this, producing the blocks, mining these blocks, we may well get the situation we have here, where two people solve the puzzle at roughly the same time without being aware of each other. And so they will send out a block onto the network thinking this is the latest block. In this case, the red block and the green block have been sent out as being the latest block, the latest update to the system, but the people producing them have perhaps not been aware of the other person producing the block. And so now we have potentially some disagreement about how our blockchain is going to proceed. And we don't want that. We want just one source of truth. We want consensus in our system so that our blockchain can proceed. And so the way we solve this is that we have a simple heuristic that we use to decide which block we're going to accept as the latest block, which one we just choose between the red and the green block here. And this is to do with the amount of work that was done to solve the puzzle. And there is always a way to calculate how much work has been done in solving this puzzle and when we're producing the block. And so the person who produces the next block, so the person who produces the brown block here, will be able to judge between the green and the red block. And so in this case, they've decided that the red block has done the most work. And so they will regard that as being the correct block going forward. They will regard that as the previous block to the block that they are producing, and they will build their block on that. And so the blockchain can then proceed, and we can then build a next block on top of that. The green block itself will be dropped, and there will be no data lost here. If there are transactions in the green block that are not in the red block, they will not be lost. They will be kept in the system. The participants in the system will still hold on to the transactions, and then maybe some will be in the red block, but maybe some of them will end up in the brown block or the blue block. But they will get included in blocks eventually. The only difference is, the only loss really, is that the person providing the green block will lose their reward. So from the point of view of the producer of the green block, they will lose out, they won't get a reward, but the red block producer will get their block reward instead. And just a point on the when we talk about rewards, in addition to the reward for producing a block, every transaction in the block includes effectively a fee. So the person who starts a transaction, so if I want to send a Bitcoin to someone, when I start that transaction, I have to provide a fee for that transaction, which is included effectively with the transaction, the amount of fee I'm going to pay. And that fee is then picked up by the miner and claimed by the miner of the block. So the miner of each block gets a block reward, which is a large amount of cryptocurrency, plus all of the fees from all of the transactions that they include in that block. And at the moment, those fees will typically be smaller than the block reward. Okay, so that's an idea of how Bitcoin and Ethereum work in terms of the consensus mechanism. This consensus mechanism is called proof of work because people are proving that they have done a certain amount of computational work. And it's important that this work is effectively useless. From an economic perspective, if there were some advantage to doing this work, then that would upset the crypto economics involved and the security involved in producing this block. But if the work is effectively useless, then the crypto economics work very well, and that secures the blockchain against people creating malicious transactions or creating blocks that would favor them, or creating spurious blocks, something like that. Okay, I must apologize. It's difficult for me to see questions, so please, if you do have questions, maybe Antonio can interrupt me if there's anything, but otherwise I'm happy to take them at the end. I think that view is perhaps, understanding that is perhaps the most difficult part of the thing that you have to understand, but it's really well worth getting to grips with that and getting the whole notion of decentralization clear, because you'll really need to be able to understand that when you're designing blockchain applications. Okay, let me just close that chat. So that's me finished with consensus mechanisms. Just give a quick history about blockchains. And the roots were in the sort of late 60s, early 70s, when we had the internet being born, and we had some big advances in cryptography. So we had public-private key cryptography and Merkle trees being invented in the 70s. And these are essential parts of the cryptography that were needed to allow blockchains to function in the real world. As soon as this technology came around, people started to look at ways of producing electronic cash and doing interesting things with this technology. But it took quite a long time. And at around the turn of the century, people started making progress also in peer-to-peer networks, peer-to-peer content distribution. We had the services, things like Napster, and means of peer-to-peer sharing. And all of these technologies sort of were around, or people were trying to use them in interesting ways. But the really big breakthrough happened in 2008, 2009, with the invention of Bitcoin. This is just a little diagram of some of the different aspects, kind of in a timeline, showing how they kind of interrelated and came together as we moved towards Bitcoin and also afterwards with smart contracts. But yeah, it was in 2008 that we had the Bitcoin white paper was produced. So written by Satoshi Nakamoto, who we don't know who this person is. It's not the person whose photo is there. They had to, Satoshi Nakamoto, who had to put out a disclaimer that he was not Satoshi. Whether it's one person or a group of people, we may never know. Some people claim to be Satoshi, and I think those claims are being seen through at the moment and being proved to be wrong. Whether it's, as I say, one person or many, whether it's an alien or a time traveler, maybe we'll never know. but it was a fantastic breakthrough. And Bitcoin as a system, I think, is a fantastic system. The fact that it has been up and running and has worked successfully for more than 10 years, and has been doing it as a public system with great incentive to attack it. The fact that it has managed to survive all of that, I think, is a great testament to its design and to the people behind it. Okay, so yeah, a little early history, just interesting aspect there. It came about 2008, 2009, really, 2009 when it was actually implemented. Commercially, it took a while to take off, but someone bought a couple of pizzas for 10,000 Bitcoins, which, I mean, the moment one Bitcoin's worth about $11,000, I think. So you're looking at hundreds of millions of dollars worth of Bitcoin for those pizzas now, if the pizza owner kept those. So yeah, quite extraordinary amounts. And in the Genesis block, an interesting thing was included by Satoshi. He put in the text. Sorry, I say he. It could be she, of course. The text for from the Times newspaper of the day that it was introduced, which was talking about the credit crisis at the time, obviously very similar to current day as well. And people often see the Bitcoin as being a product or a reaction to some of the what was happening financially at the time. Okay, well, that was the early history of blockchain and the early history of Bitcoin, it's in the early years, the 2011, 2012. So people tried to extend Bitcoin and brought a lot of other coins brought out, a lot of altcoins brought out. For many reasons, some people did this for vanity, etc., or to try and improve on Bitcoin. But the real big leap forward came in 2014 with the invention of Ethereum, where the idea was that rather than just being able to store value on your blockchain, you'll be able to do computation, and you'll be able to write things called smart contracts. The computation would be done within, effectively on the blockchain itself. Now, if you're going to be writing smart contracts, it's important that you understand really how they work in a system. And the way that Ethereum and other smart contract systems work is that they are very typical blockchains. So they are composed of nodes on a peer-to-peer network. So these nodes are interconnected. Ethereum is a public blockchain, so anybody can join and leave. They can run a node whenever they like. Anybody can interact with the system without needing any kind of permissions. But if you run a node on the system, and the nodes that are running on the system have what they do, the way they differ from something like Bitcoin, is in addition to the software they're running to keep the node going and to pass on transactions and to connect to their peers, they also run a virtual machine. And it is on the virtual machine that we have the smart contracts running. And it is the state of this virtual machine that we have as the state of our system. And so a smart contract is, you can think of it as a small application. The state of that application and all the other smart contracts that are on the virtual machine contained within our system, the state of those is what we are updating as we pass the transactions around the Ethereum blockchain. And we are coming to consensus about that in the same way that we can come to consensus about the state of the Bitcoin network, about the value of accounts on the Bitcoin network. In a similar way, we come to consensus about the state of our contracts on the Ethereum network. And so the process that happens when someone wants to create a smart contract. So Alice here is creating a smart contract. She sends it to the blockchain. So she submits the code that she has written to the blockchain as a transaction. And this is gossiped around the blockchain so that everybody, every participant on the blockchain receives a copy of her contract. And this gives great transparency to our system. So if at the moment, if you're using traditional applications, maybe you're using some application on your phone, you may trust that application, but it is a question of you having some trust in the people who produce that application. You cannot be completely sure what that application is doing as you interact with it. Whereas with a smart contract, because the code for that application is on the blockchain and is stored on the blockchain and is visible to everyone, and the computations that happen, the functions that are run in that smart contract are visible to everyone, you can be sure that the interactions that you have, you can be sure that nobody has interfered with that smart contract once it has been put on the blockchain. So it gives you a great confidence against the application that you're using being hacked. Of course, there could still be bugs in this smart contract, but you can be sure that the interactions you are having, well, that you think you are having, are the ones that are actually happening, because you can effectively see what's happening on the blockchain. The virtual machine itself is described in a yellow paper. If you want to read it, there's a link there. It was meant to be a simple architecture. There's disagreements about whether it was done in the best way, but on the Ethereum blockchain, this is what has been done. You don't have to know this very much detail yourself to use it. You really need to know more about the smart contract programming language. It is quite complex, the way that the execution model and the state is updated. There are not many diagrams out there. I found one that is quite useful. If you're interested, then you can refer back to this. If you're a complete newcomer to Ethereum, I would have a play around with it first and get a little bit of familiarity before you have a look at this. There are restrictions to what we can do in our smart contracts, and these are very important to bear in mind when we're designing our applications and when we're writing our smart contracts. The first restriction is around a thing that on Ethereum is called gas. And this is a representation of the amount of computation that can be done within a particular transaction. Because if you imagine from a security point of view, if you created a smart contract that had a function in it with an infinite loop, and you put this smart contract onto the Ethereum blockchain, then everybody would receive this and everybody would have that available on the virtual machine. Then you could, if you were malicious, you could call this function, which would mean that everybody would have to run this function themselves on their virtual machine, and which would mean that everybody's virtual machines would end up going into an infinite loop, and therefore the system in itself would effectively come to a halt. We wouldn't be able to make any progress. Because the important thing to remember about the Ethereum blockchain is that when you send in a transaction and you do some computation, that computation is carried out by every virtual machine that is on the network, by every participant on the network, which is not efficient in any way. That was my initial reaction when I heard about this, was surprised because of the inefficiency involved here. We are effectively repeating the same transaction across the network simultaneously. But this whole idea is not about efficiency. It's more about reproducibility and verifiability. So the fact that these transactions can be, you can do these transactions yourself and verify that the computation is being done correctly. So the gas is there to restrict the amount of computation that will be done in any one transaction. So when you call a function in your smart contract, there is a limit to the number of steps of computation that can be done. And this is represented by a concept called gas. And each computation, each operation that happens in a smart contract has a particular gas cost. And when you submit a transaction, when you call a function on Ethereum, up front you have to provide a certain amount of gas, and you pay for this gas using Ether, the Ethereum cryptocurrency. And this, when your function is, your computation is executing, as it executes, as each step is taken, this removes amount of gas from the amount that you provided. If that amount drops to 0, then the virtual machine stops your computation and effectively reverts what you were doing. And so this is there to stop people doing a denial of service attack in the amount of computation, or indeed in the amount of storage. If you try to store too much information in a smart contract, it would also go beyond the gas limit that you're allowed. So this is a way to secure our system against denial of service. The second restriction we have is determinism. So all of the functions must be deterministic, because we want to come to consensus in our system. We want to be sure that all of the computations we do are reproduced exactly by everybody in a system, no matter what their hardware they're running, or no matter when they run our transaction. So because of that, this makes doing random functions very difficult. If you want to create a lottery contract or any kind of game on in your function, it can be very difficult because we need determinism. And then our smart contracts are also not allowed to get data from the internet. They can. The only way you can get around this is via the use of things called oracles. The reason for this is that if you imagine our smart contract was trying to call a function to get the weather from the internet, so from a particular machine we try to call out from our smart contract to get the weather. It may be that some machines would be blocked from doing this because of firewalls, or maybe they would get the weather at a slightly different time. And at that point, we would have a break in consensus. The virtual machines would be coming up with different numbers in the functions, and we cannot allow that. So to solve that, we have oracles. So instead of the contract themselves going out to get the data, we use oracles to push data into our smart contracts. So because the oracle pushes the data in as a transaction, we know that every virtual machine on the Ethereum network will get the same data, and they will also, so therefore they will come to consensus. Okay, I'll just very quickly go through different EVM languages. You do have a choice about, when you're writing smart contracts, about the languages you can choose. The most popular, the one we'll look at today, is Solidity. And the syntax is relatively familiar to people who have done something like JavaScript or Java before. There are other ones available. If you like Lisp, there's a LLL. Viper is similar to Python. Yeah, but there are other ones available. They're not as popular as Solidity. Most contracts in Ethereum are written in Solidity. If you think about, if you're thinking about designing your blockchain project for a hackathon, and you want to know whether you should be using a blockchain, we've come up with some questions at XRP that we use when we're talking to clients to see how applicable a blockchain is to the particular use case they've come up with. And so we tend to ask these questions. It's not a yes or no answer to any of these questions. It's more a case of asking these questions and thinking about the answers. So you think about how important these things are to your use case. So how important is trust in your use case, and potentially between unknown parties? If you want to do transfer of value, this is something that blockchains tend to do very easily. Something like Bitcoin does very well. Because of a peer-to-peer network, we have a system that has 100% availability, and effectively, when you're writing your application, you can think of it as being no cost. There is obviously a hidden cost in there which is covered by, to some extent, transaction fees and by other people providing machines on the network. But in terms of your application, you can see it as being really at no cost. You get censorship and fraud resistance thrown in as a feature of the system as a whole. The data will be publicly available. So this may not suit your use case. If you have information that should be private, then you'll need to think how you are going to handle that on a blockchain, because in public blockchains, all information put on there, all transactions are public. So you'll need to think about that. Once a transaction is submitted to the blockchain, however, it is immutable. So if you submit a transaction, you cannot remove it from the blockchain. That is there forever. That provides a great audit trail. Obviously, the state of the blockchain will proceed over time, but the transactions themselves, as they're submitted, cannot be changed. So that can be seen as a great advantage to you for your use case. And in public blockchains, you can have multiple parties making updates to the system, and they may be unknown to each other, and it could be permissionless as well. They may make these updates without needing any permission in the system. If that suits your use case, then blockchains are probably a good use case for you. Okay, if we look at writing smart contracts, what I will talk about here is I've looked at Ethereum, but it applies equally to RSK. You can use Solidity and write smart contracts also on RSK. Difference being that is backed by the Bitcoin blockchain, whereas Ethereum has its own blockchain. But you can choose whichever you want to use. Just as a note that to warn you, the things that people tend to find difficult when they're starting out writing smart contracts. One of them, which has improved over the years, are the limitations of the Solidity language. It was invented for smart contracts, and it has developed over the years. So it has become more user-friendly, but it still has limitations if you're used to working with languages such as JavaScript or Java. One of the biggest problems I think you will find, one of the hardest things you will find is around decentralized design. You really will need to change the way you think about applications to take account of the fact that you're doing things in a decentralized manner, and there is no central authority, there is no central process or central source of truth in your system. There has been a lack of development tools. I mean, next week we will go through development tools, and there are some good tools out there, and things are improving all the time. But certainly compared to traditional languages, the development tools are not as sophisticated there. Okay, so let's get our hands dirty. Let's start looking at Remix. I'll just stop sharing that and instead share my browser. Okay, hopefully you can see that. So Remix is an IDE for writing smart contracts. You can use Solidity, or you can use other languages, or we're not going to cover those today. One of the big advantages that it is something that is in the browser, so you don't need to install anything. If you just go to remix.ethereum.org, it will bring up the application for you, and you can start writing smart contracts. Just to give you a quick overview of the areas. On the left-hand side here, you have the plugins that you have loaded into your session. You can add further ones by clicking on this little plug. The minimums you will need are this one, which is the Solidity compiler, and this one, which allows you to deploy contracts and run transactions. But there are other ones available that are useful for helping you with security, doing analysis of your contracts. You can do zero-knowledge proofs as well. All sorts of useful add-ins as well, but we'll just concentrate on the very basic ones here. This little file system here gives you a local, allows you to create files for your smart contract. So this is a view of some of the files I have. The one I'm going to go through today is a contract called Score, which is what is shown here on the right-hand side. So the main part of our browser here is where you write your contract. At the bottom here is where you get updates and messages when you've deployed your contract or you're doing transactions. Now I'm going to very quickly go through writing a contract. The I've got a couple of links in the notes, in the slides, to a Solidity tutorial that we have produced. So I really do recommend you go through that tutorial, which will introduce you to all, the main aspects of Solidity. I'm just going to go through them very quickly here, as we don't have a lot of time. The documentation for Solidity is pretty good. I've got a link to a cheat sheet there, but it's well worth, if you have questions, going to the Solidity docs. You'll be able to find most of the answers there. The other thing I would say is that when you're writing your contract, the compiler really is your friend. And the way I'm going to write this contract is, it's not really test-driven development, but I'm going to introduce aspects which will fail to some extent, and you can often look at the compiler messages to see why they have failed, and then fix them and proceed that way through writing your contract. So I'm going to write a contract, and it's the purpose behind this is to hold some score. It's really a very simple idea of a contract. It could represent a score in a game. It doesn't really matter, but it's just to hold a small numerical value. So we start off here. I've created a basic contract, which is completely empty. The line at the top here tells the compiler what version of Solidity I'm using. So I'm saying here I'm using Solidity version 0.7, or between 0.7 and 0.8. So that 0.7 is the latest version. We have this comment underneath, which is to talk about license. You don't have to include this, but it can be useful for people to understand what license you may want in your contract. And then the contract itself, you start with the keyword contract. You give the contract a name. So here I've called it score. And then within the braces, you have the body of the contract, so the actual code, the functions and the variables that you want your contract to contain. So initially, I want my contract to contain a numeric value. So I'm going to add that here, and I'm going to call this variable score. Now, Solidity is a typed language, so if you have a variable, you have to declare the type of the variable. So that's the thing you see on the left before the variable name. So uint256 means it's an unsigned integer of size 256. That's the maximum size for this type. You could have, if you want to make it smaller, you can. If you omit the 256, it defaults to 256. So if you just say uint, it will that means the same as uint256. So there I have my contract that is storing a small number, and that will store that number on the blockchain, and that will be the state of my contract going forward, and people will be able to update that by interacting with my contract. Now, if you look at the Solidity compiler here, I've set the compiler to auto-compile, so that every time I make a change, it will recompile the contract. If you make an error, so if I make a spelling mistake here, it will give you a warning, and it will show you where you've made the error. You get a warning on the left-hand side there, and down here you will get an idea of the thing you've done wrong. So it's telling you that you've made a syntax error. So it's useful to have that when you're typing to tell you what errors you may make. So this contract is fine, but it's not very useful because we have a score, but we can't actually interact with it in any way. So I'm just going to write a couple of functions now to interact with my score. And the first one I'll write is a thing to return the score. So from an external thing, so from say a web page, we will want to get the score, and so I'm writing a function that will return the score value, the score variable. So we could do something like this. So we'll say get score is going to return our variable here. And if you note, we get a couple of warnings. So the first warning we have is about visibility. And this is because each function that we have in our contract requires a visibility to be set. So this is really to say where this function can be called from. This is not who can call a function, but where can it be called from. So can this function be called from an external application? Can it be called from within the same contract? And you have a number of options. So the one I'm going to choose here is public. This is the most permissive. So this means it can be called from an external application or from within the contract. Please have a look at the tutorial. It goes through the different types. I don't have time to go through all of them now. We'll just stick with the public at the moment because that allows us to do pretty much everything. The second thing I have to do is to tell the function what the return type is. So what I'm going to return from my function. So I'm going to say this returns a type of uint256. So it's just this is just really the signature of the function. So we need to know the function could have some parameters passed to it, and it needs, if it's going to return anything, we need to give the type. We need to give the type of the return value. We get an additional warning here, and it's always good to check the warnings. The reason for this is that it's telling us that our function is not changing the state of our contract. And this is an important thing to bear in mind when you're writing functions in Solidity, is that you can have functions that change the state of your contract, or you can have functions that really just read the contract itself. So maybe just read the variables from your contract. Or you can even have functions which don't change the state of your contract. They don't read anything from your contract, but maybe just do a simple calculation and return that. So what this warning is doing is saying that this function is not changing the contract. And so I can put in this keyword here, view, which tells the compiler that this function is not going to change anything in the contract. It's just going to return, read something from the contract, just going to return my score variable. If you have nothing there, then it means you can change the contract. If you want it to be just returning, say, a computation, you can put in pure, which means neither change the contract nor read anything from the contract. But for this one, we're just going to have it as a view function because it's reading the value. That's great, but we need to, what we want to do next is to be able to change our score function. So I'm going to put in something to do that. So I'm going to have a function called set score, which is going to take a parameter and to make this public to avoid having to go through the warning again. And I'm going to say that I'm going to update my variable. So there I've passed in a new score, and then I've updated the score in the contract with that new value. The underscore here is just it's not needed. If you don't have to put that in, but it's traditional to do that. But it's up to you. A lot of people do that to give you a better namespace and to make it clearer where the variable is declared. So I can do that to set my score. I think I'll just very quickly go through the next thing because we don't have a great deal of time. The next part is the idea that we could publish this contract as it is, but then we would face the problem that around security, that anybody who interacts on the Ethereum blockchain could potentially change the score in our system, and we probably don't want that. We probably want to restrict who is allowed to update our score. And so to do that, we have things called modifiers. And what I'm going to do for this, and I'm not going to go into a lot of detail around this, we don't have time, but I'm going to have a variable of something in the contract, so an address, So this is really an identifier, which says that someone in our system has special rights. So we're calling this person the owner of the contract, and they have special rights. We're going to allow them the right to change the score and restrict changing the score only to this person. And in order to do that, I introduce this thing called a modifier, which I'm going to call only owner. And the syntax for this is slightly odd. There are different ways to write this. I'm going to do this in a way that is more explicit, but you will see ways that are sort of neater than this. So you can take shortcuts, but this is more explicit about how it works. So just to explain what I've done, what this modifier says, the way to think about modifiers is to think that they wrap around a function. And the way they wrap around the function is that they effectively, you put the function into where this underscore is. Now, the function I want to be modified in this way is this set score function. So what I'm going to do is apply this modifier here. So I say this function now is being modified by this modifier, only owner. And effectively what this is doing is wrapping this modifier around this function. So whenever somebody tries to call this function, they effectively have to go through the modifier first. Now what this modifier is doing is checking the person who is calling this function. Now this msg.sender is a global variable that is available to you in your contract and gives you the address, the identity of the person that is calling this function. So what I'm doing is I'm saying, if the person who is calling this function is the owner, and this owner is something that I have set up in my contract, if the identity of the person calling this function is the special person, this owner, then I'm going to allow them to proceed into this function. If not, then I'm going to skip out, so they don't actually call this function. So if they're the owner, they can set the score, they can put a new score in and update our score variable. If they're not the owner, they won't be able to set the score. And so in that way, we have a very simple way of doing some kind of security within our contract. The other things I'm just going to mention very quickly. You can also signal that events have happened, that things have happened in your contract by having things called events. Now it may be that I want to know when a score has been changed. So I can create an event here, which I call score set. And in my function here, I would emit this event. And the reason for this is that, let me just write this. The reason for this is that there is difficulty if you're calling one of these functions externally. There is difficulty in the nature of the way that the transactions happen on the blockchain. So you will try to call the function as a transaction, and that transaction will be submitted to the blockchain and will be passed around the nodes, and eventually will get mined, put in a block. That block will get passed around, and only when that block is applied to each virtual machine in the system will the transaction actually run. And because of that, it's difficult for the person calling this function to know whether this has actually happened or not, because it could be a number of seconds before it happens. And so to assist with that, we have this idea of events. So here in my function, when the function runs, I'm going to emit this event, and events can be thought of really like a log within your blockchain. So it emits this event, which is kind of like logging that something has happened, and your external function can effectively poll this log and can see when that event has happened and then can react to that in some way. So it sends off the transaction, and it waits around. It's not really sure what's happened, and then it monitors this log, waits for the event to happen. When it sees the event, then it can proceed and say, okay, the score has changed. I'm going to go and do something else. But we can go into that more detail next week. There are other types in Solidity. The most common ones are mappings. These are like dictionaries in Python, or things like hash maps in Java. And they just act as key value pair structures, key value pair types, and they need a type name, so I'm going to call it score for user. So here we have the key would be an address, and the value would be a number, a uint256. The thing that gets most people is that the keys are not available separately. So if you add things into a mapping, you cannot then iterate through the key set. So if you want to keep track of what has been added into a mapping, the keys, then it is best that you put those into an array, and you can create an array of all of the usual, all of the types that you have in Solidity. Okay, I'm going to leave that there. Please have a look at the tutorial that is online. We go through all of this in much more detail, and certainly do ask questions. I'm going to go back to the slides now, so I'm just going to stop sharing this. Instead, I'm going to share the slides. There we go. Okay. There's the links for the Solidity tutorial, and some documentation about Solidity. So yeah, please have a look at those. There are great libraries around. There's a project Open Zeppelin that has common libraries, libraries for the common contracts that you'll use. So it's really worthwhile checking before you write a smart contract to see if it's already been written by Open Zeppelin. And lots of people have had their eyes on these contracts. It's open source, so it is very safe to use these contracts. Yeah, I would definitely recommend you use these if possible. Just to finish off with, I wanted to talk very briefly. If you're designing an application, it's often difficult to get your head around the difference between decentralized and centralized systems and how to adapt them. I just want to take an example of a game here. We're talking about developing something, because if we were playing a game with a centralized system, something like rock paper scissors, is very easy to write a game to do that, and to have some centralized system keeping track of the game and keeping track of the players and the moves that they are making. If we try to do that in a smart contract, we run into a number of problems. So a naive implementation of that, if you imagine Alice and Bob are wanting to play rock, paper, scissors, naively you may imagine that they would make their moves by putting a transaction into a smart contract. So Alice perhaps would play rock, but the problem there is that all of the transactions going into a contract are visible on a public blockchain. So as soon as Alice makes a move, then Bob can see Alice's transaction, and so he will always know how to make a winning move based on that. So here he could make a paper transaction, and he would win this game. So in that way, the smart contract would give him a prize, and it's not much of a game. But we can improve on that to some extent by using cryptography. We could make Alice, instead of sending in plain text her move of rock, she could send in a hash of that, a fingerprint of the move, and by doing that, she is committing herself to that move, but providing something that is not as easily readable for Bob. So let's imagine here that Alice does that. Bob will see that the transaction has gone in, but he may not realize what that transaction represents. So he also makes a transaction. So he commits to his play, which is scissors, and sends his hash for that. Then the next step they make is that they go into a reveal stage by revealing their plain text move. So here Alice says that the move she made initially was rock. Bob reveals that he initially said scissors. And because initially they've made the commitment by sending in a hash, they cannot lie at this stage about what they've done. They have to be honest about the move they made initially. Otherwise, the hash would not match the transaction they're sending here. And then the smart contract could judge both moves and decide upon a winner. There are still problems. Obviously, Bob could look at all the possible values that could be used in the game and work out the hashes of those and use that to read what Alice is going to do. So you would have to put in extra checks and extra things here to allow the game to be played. But what I wanted to really say here, just is to give you an idea of the difficulties involved sometimes in moving from a centralized idea of a game into something decentralized, particularly when it's in a public blockchain where people can see the interaction. So you will need to bear that in mind. So that's covered very quickly, everything I want to do. We have more workshops coming up. So next week, my colleague Tom will be taking Solidity further and showing you how to build a DApp and everything you need to build a DApp in a hackathon and interact with it from, say, a web page. The following week, we'll talk about security and smart contracts. And on the final week, we will give people an introduction to zero-knowledge proofs, which is an incredible technique for introducing privacy and verifiability into your transactions. If you have questions, there are some contact information. So please do contact me if you want to. We have a number of blogs around different subjects as well. I'm sure you would find those interesting. You can email me or message me on Twitter. I'm happy to do that, or I'm also happy to take questions now if you have any. Let me just go back to that slide. I think I'll probably need the chat here, don't I? Okay. Yeah. I'll make Antonio host. Right, I'll have a go at that. I'm going to stop sharing, maybe. Good. You've done that.
Hi, Laurence. Can you hear me?
I can, yes.
Excellent. So how much time do you have to have a live Q&A session?
I think I have a fair bit of time, actually. I'm really happy to stay here.
Oh, perfect. Excellent.
I'm sorry I did run over.
Yeah, that's okay. That's all right. That was a very informative session on the introduction of blockchains, Bitcoin, Ethereum, and even coupled with hands-on Solidity. So that was a really, really informative session indeed. So now what we're going to do now is allow for Q&A. What I'll do is it's probably best if I enable people to be able to unmute themselves. We didn't get that many questions earlier. I think there were only about 3. So.
Oh, okay. Well, I'm happy to stay around if people have questions. So yeah, please do feel free to ask anything.
So who would like to fire away with the first question?
Hello, Laurence.
Hi.
Hi, it's a very great session. Thanks for it.
Thank you very much.
This is the first time I have a hands-on live demo from you on the Solidity. I'm seeing it. It's a very great session.
Okay.
Just how to write a small game, what you showed as a rock scissors as that. How we can write as a game with the contracts, does I come to know with this?
Yeah, so a couple of things that you will have problems with, I think. So I think a couple of things to bear in mind. One, which is what I was talking about really with rock, paper, scissors, is the fact that the moves in a game can be, if you do them as transactions into a smart contract, and you're doing this on Ethereum or a public blockchain, then those moves can be seen. So if that is going to be a problem, then you may have to find some techniques to maybe disguise the move that is happening. It is also in a game, because the transactions, they may not complete for say 15 seconds because of the
Yes,
block time.
the time limit.
So
Yeah.
it may be that may be too slow for you. So one thing you may have to do is to have part of your game off-chain. So you may want some centralized part that people can interact with and that is quick enough for them to interact with, so that the game, doesn't feel, really slow and horrible. But then have some aspects of the game that are on-chain. I know a lot of games have used smart contracts to store things like in-game assets. So if you have some in-game currency or something of value, maybe those will be stored on the blockchain in a smart contract, because they're transacting with those you don't have to do very quickly. But the thing that the actual gameplay itself, which has to be quicker, maybe you would do that off-chain and do that in a centralized way.
Yes. Okay. Sure. I will follow that. Thank you.
No problem. Thank you.
We have a question from OnePlus. OnePlus, if you could unmute yourself. So the question was, Laurence said that data will be publicly available. Can we use cryptography to privatize some of the data, like user identities?
Yes. So one typical thing people do if you want data to be private is maybe you would encrypt that data before you include it in a transaction, and then if you used a suitable encryption scheme, then typically that will look like random data to anyone else on the blockchain. If you think one thing that it does cause problems are the GDPR requirements. Whether encrypting data is enough to get around those is a moot point, and different lawyers I've spoken to have different views about that. It may be that you have to store data off-chain instead, and perhaps store a reference to it, maybe a hash to that data, store that on-chain. Really, generally speaking, if you have a lot of data or you have private data, it may well be better to store that off-chain and only put into a smart contract the very minimum that needs to be in the contract. It's often better to have maybe the computational part in the smart contract, so that people can verify the computation has been done correctly, but store data elsewhere. And next week, my colleague will be talking about an option to do that when we talk about IPFS, which is a decentralized file system. I hope that answers your question.
Yep. Laurence, someone asked earlier, will blockchain compete with AI or complement AI? So you've done some work around that space before, and the intersection between the various different emerging technology with blockchain. So can you just give an overview for that one?
Sure, yeah, that's a very interesting area. There are some projects now out there that do this to some extent, but one of the, for those of you who are familiar with AI, it's things like, say, neural nets. I mean, typically, if you're training some AI, it requires very efficient computation, and that is something that blockchains do not do well. So that often has meant that AI and blockchain have not mixed very well, and that only certain aspects have sort of come together and been mixed. So, but there are some projects that do that, and as usual, I've completely forgotten the names of these off the top of my head. They'll come back to me. But so some people have used, for example, blockchain to store the results of computation that has been done by AI. So if you have something, maybe the AI is there to make some decision or to do some computation, and that could be done off chain, but maybe the results from that are then stored on chain, or maybe even the mechanism or the computation itself is visible on chain so that people can have confidence in how it's being done. And this interacts with areas like federated machine learning as well. The other way, an area that we're interested in and we're developing in a project that we're involved with, is the idea that the AI is used to monitor the blockchain. So it's not used to, you're not using AI in a more general sense in the blockchain, but that an AI is being used to check the blockchain for integrity, for performance, and for check that there's no malicious behavior going on. So there are some very interesting intersections there, but excuse me, because of the some of the performance difficulties, it can be quite difficult to merge the two. If you contact me later, I can point you at some projects that are going on in that area.
Hello.
Well,
Am I audible?
right.
Am I audible?
Yes, you are. Please
Yes,
go ahead.
yeah.
Yeah. Actually, I'm an engineering student, and I'm working on a project in blockchain. And the purpose of the project is the main topic is product grading system. So I'll just explain. Like, product grading system basically is like, suppose when you're purchasing a product on Amazon, Flipkart, or any other, or any site. So there, as a purchaser or as a customer, when you want to see a product, when you want to judge a product, so you look at the reviews, right? If the reviews are correct, and if the product has great reviews, then only will you go ahead and buy the product, correct? But my project, the project that I'm working on, is that through blockchain, I want the customers to get proper transparent feedback from other customers, and it shouldn't be manipulated, because some companies, what they do is they manipulate the reviews, so that, and they trick the customer into buying the product. So
Yes.
I'm working on a product on that project, so I want to know, how do I go about the smart contract using Ethereum virtual machine?
Yeah, that's a great project, great idea. So yeah, I think you have a couple of things you'll need to think about. So in terms of the reviews themselves, blockchain is going to be very good. It gives you an audit trail. So if somebody submits a review, then if you store that as a transaction, or the transaction from that will be going to the blockchain. You can store either the review itself, or perhaps a link to the review, or a fingerprint of the review in a smart contract. Then that means that, you know, afterwards nobody can go in and interfere with that review or change it or delete it or anything like that. So that's a great thing to do. I think one area that is more difficult is around the identity. So how do you stop people creating multiple identities and fake identities and submitting multiple reviews that are perhaps not accurate? And to address that, there are a number of projects in the blockchain world that deal with identity. And you know, I'll leave you to look these up. But things like there's also the idea of decentralized identifiers, which is a whole other area. But the idea behind that is that if you have some system like that where you can create an identity online, then that can be used as really as an anchor to your review, and you could. And maybe you would have a reputation system as well. So perhaps an identity is set up, and other people who could verify perhaps that identity is genuine, or maybe they would say that you know, this reviewer is talking rubbish, and they would decrease the reputation, and all of that could be put into a smart contract. So yeah, there are a number of aspects there that I think you should look at. So identity systems and reputation systems, I think, will certainly help you with that.
Actually, so hello.
Hello, yeah.
Yeah. So is it like, can we use Java in this? Because I am not aware of Solidity at all. Like I need to learn that language altogether. But I'm familiar with Java. So how do I implement blockchain in Java?
So yeah, if you're writing it on Ethereum, I would you have to use Solidity or one of the other ones I mentioned. I it's close enough to Java that I think you should be able to uh, to use it reasonably well. The syntax will look familiar to you, and some of the concepts will be familiar to you. But yeah, I would recommend Solidity. There are reasons that we cannot use traditional programming languages on Ethereum due to things like determinism and gas as well. We cannot go directly use things like Java and all the Java libraries on the Ethereum blockchain. So yes, you'll have to try Solidity, I'm afraid, but it's I think if you know Java, you'll not have too much difficulty with it.
Thank you, sir. Thank you so much.
Thank you.
Does anyone else have any question? Okay, we had a question earlier, Laurence, from Saypercent. I think this person is still here. The question was, what is the purpose in building consensus? Is it mandatory?
Okay, so yeah, the whole blockchain really is built around this idea that the state of the system at any time is achieved by the consensus of the people who are involved and who are using our system. If there's a break in consensus, effectively you get things called forks, where so maybe one part of the network decides that their view of the system is one particular thing, and another part of the network thinks that the system at that particular time is something else. And unless that's reconciled, then really you end up with two separate systems there. So yes, so blockchains are very much about achieving consensus amongst the participants, and that part of that then ties into the security and into the confidence that people have that the system is running fairly. The fact that if you're using Bitcoin, that your balance is being updated in a way that is visible and is being checked by and supported by people who are complete strangers to you and have no interest in your balance, so have no interest in either doing anything malicious to you or to helping you out. That gives people a great deal of confidence in sort of and the impartiality of the system.
Well, thank you so much, Laurence. I think we should end it there. Mm-hmm. We're about 20 minutes over. Do you have any final comments, Laurence, for individuals and teams that are kind of going about building solutions during a hackathon? We have a lot of developers that are fairly new to this space. Having conducted and mentored in various different hackathons before, what's your key advice for them?
Yeah. So first of all, yeah, I'm sorry for going over, and thanks everybody for attending. And good luck. And really, yeah, I'm sure you'll enjoy the hackathon. My advice really is to think in a decentralized way. That's perhaps one of the hardest things. So get really think of how your application is going to work without a central authority. And it may be that you have to then think about game theory and crypto economics, things like that. But those thinking in that way will really help you solve the problems. And it may introduce you to ideas that are absolutely unique and people haven't thought of before, and to some really exciting novel solutions. And I really look forward to seeing them.
Thank you so much, Laurence. And Laurence and his team are available to answer questions on Slack. Mm-hmm. They have volunteered to be mentors and judges. So if you have any questions, please post them there. And thank you so much, everyone, for joining us. And once again, Laurence, thank you very much.
Thank you.
I'm going to stop the recording now and end the call. So I'll see you everyone on the next session. Thank you so much. Thank you.
Thank you, guys. Thank you. Bye-bye.